Okay, so let's continue Anderson localization problem. So yesterday we formulated this perturbed expansion order by order in this potential, scattering potential V, which is the local impurity scattering potential. And we made the approximation that this potential is extremely local, so that this can be represented by a Dirac delta peak. Okay? And we need to perform this disorderly averaging or ensemble average of all possible configurations of this impurity positions. And up to second order, these are the results. Okay? So the first order, we have just a single potential scattering term. At the second order, we have, say, two dashed lines representing two different scattering processes. And we haven't performed this impurity, say, averaging yet if I make such a plots like this. So after this impurity averaging, we put the sort of a bracket for this diagram that we would like to perform such an impurity averaging. And if we look at this, the first order term right here with a single dash line, and last time we mentioned that when we perform such an impurity averaging, what we do is to evaluate this term, sum over L, where L is the position of this impurity, okay, this exponential phase factor, and you sum over all possible impurity configurations, and that's how we did. Okay, and we assume further a simple distribution, which is a white noise distribution, meaning we have an equal probability to find this impurity to be any place on the lattice. So the first order impurity averaging gives you this delta Q of 0 times this number of impurity, and which is given by this diagram there. So after we make such an impurity averaging, we put a cross right here at the vertex of interaction vortex point. And so you could very easily see that this term vanishes if Q is non-zero. So this term survives only when Q equals 0. And this is the zero momentum transfer scattering, right? So, and in a minute we will show that this only shifts the chemical potential of the metal, so we could redefine our chemical potential, and so this term, this contribution, does not play any role. Okay, in any physical observables, you don't see the contribution because it only shifts the chemical potential. So let's just perform this impurity averaging of the second term right here, where we have two dashed lines, and we'll see that this will give you some contributions. All right, but this zero momentum transfer diagram could be generated up to second order, third order, up to infinite number of orders in this perturbed expansion. If we just consider this zero momentum transfer diagram, we could have this single dash line with a cross and Q equals 0, and we also have these two dash lines, but Q also becomes 0 on both, this interaction vortex. So, and we can sum over all such a zero momentum transfer diagram, and all of this diagram do not contribute. So let's just look at this second order diagram. When we perform such an impurity averaging, of course you have such a zero momentum transfer diagram. As I mentioned, we could neglect such a zero momentum diagram. We only keep this finite momentum diagram, and let's just do it. So of course, in the thermodynamic limit, we need to, where this volume goes to infinity, of course this impurity averaging should carry a volume factor in the denominator when we really calculate this physical observable. So this is given by the density of the impurity. Okay, so we could do the same thing for the second order diagram. So this is given by the product of this two to density, right? Rho I Q1 and rho I Q2. So when we perform such an impurity averaging, we simply just plug in this definition of this impurity density term, which is the phase factor. So remember, this Q1 and Q2 are both independent variables, and so are L and L prime. So you could imagine that we have four different terms, or two can be categorized in terms of two classes of terms. One is when L equals to L prime, another is when L is not equal to L prime. So you could imagine I could just classify this product, these two summations. And let's just separate this to contributions. So if L equals to L prime, and we can actually sum over all these exponents appearing right here and there, and there's only one summation. We can also have this, the term when L is not equal to L prime. So then we simply just perform such a summation, and when L equals to L prime, and you sum over such a phase factor, and the result is just, again, another Kronecker delta function. Delta Q1 plus Q2 and 0, which means that when this Q1 is not cancelled by Q2, you get 0, but you get 1 if Q1 is minus Q2. And the prefactor is number of impurities as usual. What about the second term when L is not equal to L prime? Well, you simply just pick, you sum over these two different indices, and the result is simply equal to the product of two separate Kronecker delta functions for Q1 and Q2, since L is not equal to L prime, so that you pick any two of these, say L's, and of course you don't pick the same L, right? L is not equal to L prime, so therefore you got this many, say, terms. So you choose, one from Ni possible, say, sites, and then you choose another one which cannot be the same as the one that you already picked. So you get one option less, right? So Ni minus 1. So you simply choose two out of these two groups, L and L prime, but L cannot be the same as L prime. So this is the number of ways that you could choose. Okay, so but each of them, when you sum over this L and L prime, you get this conservation of momentum, so that you get two separate Kronecker delta functions. So again, in the thermodynamic limit, we need to divide everything by this, say, V squared, because this is second order term, right? So this impurity average over this product of the two rows at different momentum, Q1 and Q2, leads to such two contributions. So the first term is given by this impurity density little ni multiplied by this Kronecker delta function, delta Q1 plus Q2, when Q1 and Q2 are both non-zero, but Q1 equals minus Q2. So the second term in the thermodynamic limit is approximately given by little ni squared, because this capital Ni is much larger than 1, okay, because both the volume and the number of electrons approach infinity, so infinity minus 1 is infinity. Okay, so this is little ni squared times these two separate Kronecker delta function. Okay, so diagrammatically you could make such plot. The first one is a little triangle where this one of this potential carry momentum q and another carry momentum transfer minus q, so that they actually get cancelled. So this is V of q, this is V of minus q. But then you need only to multiply this density just once times little ni. So what about the second term? Well, the second term is the same as that one. Okay, we already expected, where you get two separate dashed lines with two separate crosses, and they do not interact with one another. So you get two zero momentum transfer scattering processes, and each of this vortex carries a prefactor ni. So you get little ni squared, and these two crosses do not cross. But the first term, where you have just cancellation between Q and Q2, you do have a single cross, because these two merges right at this intersection where Q1 actually got cancelled by Q2. So in other words, the first term carries the single cross, but the second term carries two crosses. And as we argue already, that this two decoupled scattering, we could sort of ignore this, because this only updated this chemical potential and shift the chemical potential. And so we simply just forget about this, and we only consider this term. So then we could continue performing this impurity averaging over the higher order terms. For example, if you have the third order term where we have three dashed lines representing three different scattering processes by impurity potential, and we can imagine that we have many terms like this would have reappeared, but we have a major contribution, a new contribution coming from a single cross which connects three interaction potential terms, and they actually get cancelled, right? So this Q1, say Q2 and Q3, Q1 plus Q2 plus Q3 is 0. And we also have a single triangle with a decoupled single dashed line and the permutation of two other terms like this. So this is also a possibility. And we also have this three independent dashed line, which we will neglect. So we could combine all these non-trivial diagrams and to make a total full Green's function. So this is the Feynman diagram representing all these terms that we obtain. So some of these dashed lines actually cross the other dashed lines. Some don't. As I mentioned, we do not care about this decoupled dashed lines, but we will discuss how to organize all these diagrams and which terms or diagram is more important than the others. And we can imagine that we have different variations of this sort. For example, we may have this is just say up to third order, but we can imagine that we have even higher order terms like this, the fourth order, and maybe we have this so-called crossing diagram. So these are all possible contributions to the full Green's function, and we will discuss these different contributions later. Okay, so let's take a short break. When we come back, we will continue just to sum over all these contributions, and we'll try to find out the self-energy of this electron Green's function, due to this impurity scattering. So let's continue. As I mentioned, this single dashed line with a cross represents the shift of chemical potential of the conduction electron. So by adjusting this chemical potential of the conduction band, and we could actually renormalize it so that this V of 0 is 0. So we could simply just adjust our energy reference point so that this term will go away. So we can always do that. Therefore, we don't care about this dashed line, and any diagram including this single decoupled dashed line will not contribute to this full Green's function. So now we could connect all this so-called connected diagram up to this lowest non-trivial orders. We have this single triangle, and a triangle with the three dashed lines and intersecting two triangles like this. And you can imagine there are many other possibilities to form this complicated triangle. And to simplify this calculation, we only consider here so-called Born approximation, which is a single triangle. This is the lowest order diagram, and called a Born approximation up to the second order impurity scattering. So of course, all the other complicated triangles could contribute to the self-energy, but we don't include that. You may wonder how important they are, so you could do some homework exercise to convince yourself that in some situations we could safely neglect all these terms, only keep this leading order term. And so this is approximation. Of course, this approximation needs to be justified, but in the literature, people only consider this Born approximation, so which we call the sigma 2. This subscript 2 here represents the second order contributions, and this is the lowest order contribution to the Green's function. So in K and omega space, we have this diagram, and remember this two momentum Q1 and Q2 got exactly cancelled. So this is Q, and this will be minus Q. Okay, so we can now try to evaluate this triangle from the definition of self-energy and the Feynman rules, the Feynman diagram. We are able to integrate it over the internal degree of freedom, which is p prime. An electron comes in and it gets scattered by this impurity centered around here, and then the outgoing electron or intermediate stage electron carry momentum p prime, and then it suffered for a second scattering, and after the second scattering, this electron carry the original momentum p again. So this diagram represents such a second order scattering processes from p to p prime and back to p. So how do we do this? So we simply just follow the definition. So we sum over the internal degree of freedom by Feynman rules, and this internal degree of freedom is p prime. And inside this triangle, the solid line represents this bare electron propagator G0, carry momentum p prime, and this matsu bar frequency I omega n. And of course we need to include this V potential term, but in the second order we get two factor of V. One is V of Q, another is V of minus Q. But we know that from previous lectures that this V is actually a real function. So V of minus Q is actually V of Q star, where star represents the complex conjugate of V of Q. As a result, you make a product between Q, V of Q, and V star of Q, you get absolute value square of the V of Q. And from this local approximation, we know that this V of R is simply just Dirac delta function, which immediately tells you that the V of Q is just V0, it's just a constant. So the Dirac-like local impurity potential is very sharp. So the Fourier transform V of Q gives you just a constant prefactor. So now we plug in this constant V of Q, which is V0 square, and now we get to this, which is little ni, three-dimensional integral over p prime and V0 square, and 1 over I omega n minus epsilon p prime, where epsilon p prime is the excitation energy of the bare electron band, which is simply just a quadratic band for electron gas. So then this is the simplest possible example of the self-energy that we can perform analytically. And after this momentum integration, and we could take the analytic continuation going from the matsu bar frequency to the real frequency plus or minus I eta. And this is the sigma or self-energy in real frequency and momentum. And then we plug into this Dyson type equation to get this Four-Green's function, just based on this infinite series of this single triangle. So if we consider just a single triangle, and we could imagine that we have many triangles, but each of this triangle is independent of the others. And we sum over all such triangle-like diagrams without crossing. So once you cross this triangles and you calculate different diagrams. And this is, in some references called the non-crossing approximation. And G italic inverse is G0 inverse minus sigma 2 K and I omega n. And you can make analytic continuation by this identification, and then you go from G italic to capital G, and then we're done. Well, just part of the story, and this is the calculation for the electron scattering rate or relaxation rate, which is proportional to imaginary part of sigma 2. And the relaxation rate is inverse of the relaxation time, where this relaxation time tau tells you how much time is there between any two collisions. So this is the time that electrons are free of scattering. So on average, how much time does this electron actually get scattered by this impurity? And inverse of that so-called mean free time defines the relaxation rate. So
I think for the first order, okay, I say that because you have several mountains, if I say that triangular, it like there's no lake, but others you have lake. So I think the diagram, first the triangular diagram should be have two lakes, right?
Yeah, of course.
Okay, thank you. And we will have a self-energy also do that kind of approximation. So the self-energy, can we say that the retarded self-energy or advanced self-energy?
Yeah, of course, depending on, this is plus or minus. So we defined this retarded advanced Green's function from this analytic continuation before. You check your lecture notes. Okay, so this is the simplest possible example of self-energy we can imagine in this Anderson disordered metal problem. And we'll come back to this relaxation rate calculation in just a moment. So let's take a short break.
Another question is, can we make sure the imaginary part of self-energy always greater than 0?
Well, this is a good question, but you will see. At least in this case, in this particular problem, we do have, from our definition of a sigma, the positive value of the imaginary part of the self-energy. Well, you could check this for different systems yourself, and in general, of course, you could have the situation where you have a negative imaginary part of self-energy, but this will become the troublemaker. So then, you don't have an exponential decay of your quasi-particle weight, Green's function, but exponential increase. So physically, this is not possible. Mathematically, you can imagine that you have both positive and negative value of the imaginary part of sigma, of course. Well, then we should study different systems case by case. At least this simple situation that we have here, it should be positive. And this is the thing that we will do right now. Okay, so let's just do it. Let's try to evaluate this real imaginary part of the sigma, or sigma 2, in momentum and real frequency domain. So we already analytically continue in this multiple frequency. Of course, there are two choices. One is the retarded and advanced, the other is advanced, but we don't specify this, and we will specify this retarded advanced self-energy of Green's function in just a moment. So this is a general sigma, and this epsilon p refers to the excitation energy of the free conduction electron band, and we could shift this chemical potential or Fermi level, and in the t equals 0 limits, we call this chemical potential 0 or Fermi level 0. So we just redefined our energy reference point to the chemical potential or Fermi level so that the Fermi level is 0. So of course, in general, this sigma 2 can have the real part and imaginary part. Okay, so let's look at this imaginary part first, which I call this sigma capital I in the subgroup. So this is given by omega minus epsilon p minus real part square plus sigma I square and sigma I. And I call this sigma real and this sigma I. And you can see that the full self-energy, so this is the full self-energy, is given by this Green's function, right? This is G4 or G4. So this is so-called Dyson equation that when you sum over all such single triangle diagrams or connected single triangle diagrams, and you get the full self-energy. And this full self-energy, by definition, you could just plug in this G4 on the right-hand side of the integral. And of course, you can say that this sigma is the same as that sigma. So you need to really solve this Dyson equation iteratively and until these two results on both sides of the equation agree. So this is called Dyson equation. And we simply just take the imaginary parts on both sides of the equation, and this is it. And then we try to evaluate this momentum integration, and we convert this to the energy integration, assuming a constant density of states at the Fermi level. So this is a common trick that we often played in solid state system. So we convert this momentum integration to the energy integration by assuming the constant density of states at the Fermi level, and capital N as function of epsilon f refers to the density of states at the Fermi level, which is constant. So you could very clearly see that this sigma I, which is the imaginary part of the sigma, appeared on both sides of the equation, and at least these two just cancel out, and we could simplify this equation in the imaginary part, which is given by this. Suppose this epsilon refers to, x is actually your epsilon, energy, epsilon p. Sorry, this is omega minus epsilon minus the real part. And the energy integration ranges from minus to plus infinity, and you actually shift your lower and upper bound of the integral by this omega minus sigma r, but we know that both omega and sigma r are finite, so it doesn't matter. Omega plus a finite is also omega minus omega, negative omega minus or plus any finite number is also minus infinity, so this upper and lower bound of the integral do not change. So by change of variable like this, and this is the remaining job that we need to perform, which is a simple integral over the x. And you could easily check the table of integration, and this is simply just this result right here. So you get some arctangent function once you perform such a dx integration, and from plus or minus 1 pi over 2, so you get pi divided by this sigma I magnitude. On the left-hand side, this is 1, because this sigma I on the left-hand side of the equation is already cancelled out by this on the right-hand side. So on the left-hand side of the equation, you get 1, so immediately you get sigma I, right? What is your sigma I then? Ni V0 square density of states at firm level times pi. And we define this as 1 over 2 times the mean free time, tau. So you can clearly see that this imaginary time, whether this is positive or negative, I think only the magnitude actually matters. So you get scattering time, which is inverse of this. Of course, it is positive, right? Because tau is defined by the magnitude of sigma I. It doesn't care about the sign. And this is true because when we integrate over the x of this integral, and automatically this magnitude of sigma I appears, it doesn't matter whether the sigma I is positive or negative. So now let's just look at this 1 over tau in momentum space. Remember, this 1 over tau I defined here is the so-called the average scattering rate, where you already perform such energy or momentum integration, which you average over contributions from all momentum that carried by the electrons. So you count all contributions that come from different electron carry different momentum near the Fermi surface, and this is kind of an average quantity. But you could also define the quantity at a particular momentum k near the Fermi surface, so that at particular momentum k you get the scattering rate or scattering time associated with that particular momentum. Okay, so this is meaningful when you measure the scattering rate in momentum space. For example, if you carry out the scattering of electrons or photon and of some materials, and of course the scattering events are done at particular momentum and frequency, so that you could really see this scattering rate at a particular momentum. And this is defined as this quantity over here. So which means that you sum over this k prime or internal degrees of freedom, but this external leg, remember this external leg, which represents this electron propagator carrying momentum k, and this is still there. Okay, so in general, this is the thing that we need to carry out. But for Dirac-like delta potential, as we mentioned, this is just a constant. So this is V0 square. And you plug in this V0 square and times this Dirac delta function, which tells you exactly the momentum that you have such a scattering, which means that this epsilon k should be equal to epsilon k prime by the energy conservation. So then this immediately tells you that this is also a constant. This is a constant only for delta potential. In general, this is not a constant, okay, for arbitrary potential or in other problems. So we could make a plot, so-called spectral weight, but let's go back to the real part of the sigma that I didn't mention. over there. So you could do the same thing for the real part. It seems like it doesn't matter too much. And we could show that the real part of the sigma vanishes. So we follow the same rule that we calculate sigma I in sigma r, you get this integration, right? So again, so you could just change this to, you can change your variables, right? So you'll get something like x squared plus sigma I squared, something like that. So you could easily see that, okay? And again, this is 0 because you got exactly cancellation between this positive and negative branch of this integration, right? So this x squared here in the denominator is actually even function of x, but there is an odd function x in the numerator, so which exactly cancelled between plus and minus x when you perform such integration. As a result, this effectively is 0. So you don't care about the real part of the sigma, and only the imaginary part of sigma survives. Okay, so let's take a short break. When we come back, we will continue making a plot of this momentum-dependent scattering rate and also the so-called spectral weight of this Green's function, including the self-energy correction.
Here, why is not the kind of strategy if you already write down according to the Feynman diagram the one triangular, and then we do the infinite, this kind of a proper self-energy, and then do the infinite summation to get a self-energy and use this strategy to calculate.
So what's your question?
My question is, for the previous lecture, you tell us proper self-energy, then we can get a self-energy. But it seems you, I don't know why this problem we cannot use the same chip to do that.
Of course, we sum over all triangle, right? So, as I mentioned, you have infinite number of triangle diagrams in principle, right? In this geometric series, and we sum over all of them, right? And this is what we did.
Okay, but I think you use another way to do it, right? You didn't really do the summation because we didn't see a kind of a...
Well, you could see it's a very simple exercise. When we write down this Dyson equation, this implies that we already finished all this calculation that we did before. That's the final answer. I can skip this, steps, right? In a way, we exactly did what we have done, just that I skip the steps. Okay, so of course you sum over all this infinite number of triangle diagrams and you get this full Green's function, and you can define this full self-energy in the same way. Okay, any other questions? And later we'll see that the self-energy corrections can only give us this scattering, relaxation rate, and to get this Anderson localization result, we need to go beyond self-energy, and we should consider a different correction called vortex correction, and this vortex correction will be introduced later, after we finish this self-energy calculation. Okay, so, but you could imagine that this is the simplest example you could imagine, applying this Feynman diagram, Feynman rules, but then the results are not that trivial. As you see later, that when we include the vortex corrections, this calculation still relied on the self-energy that we calculated today. Okay, so because the self-energy correction really updates the Green's function of a single electron propagator. Okay, and the vortex correction are based on this fully dressed, renormalized Green's function, the full Green's function, in a non-trivial way, so that you will have this localization phenomena. Okay, so let's continue. So imagine I could look at this impurity average, say G italic, which is imaginary time Green's function in the Matsubara domain, and after this impurity average, we get the full Green's function, right? And this is the expression for this G italic full, but of course we could convert this to capital G full, which is this form. And remember, there is a sine function, or sine function reports +1 when x is positive and -1 if x is negative. So here is the homework, just derive the sine function. So you could perform such a self-energy calculation, and you assume that omega is positive or omega is negative, and then you could derive such a sine function. As I mentioned, this sigma tau of 1 over tau k is just a constant for a delta potential. And we could define this G retarded and G advanced Green's functions based on this imaginary time Green's function, or gk italic g full ki omega. So let's just define this G retarded and G advanced, which we'll call this capital G plus. Remember from the spectral representation, we got this integration over omega prime, and this 1 over omega minus omega prime plus I eta in the denominator, and we have the density of states, a spectral density, rho as function of omega prime in the numerator. So you follow this definition of the G retarded and also the advanced. So we could take this impurity average on this both retarded and advanced Green's function. For retarded, we get plus I over 2 tau, and we can do the same thing for capital G minus, which gives you G advanced Green's function. And it doesn't matter whether you use G retarded or G advanced, the decay of the quasi-particle can be easily seen by Fourier transform to the real space or even to the time domain. So the total Green's function is actually short-ranged, and it is limited by the mean-free path, which is defined as little l here. So you can show very straightforwardly that this impurity average Green's function, whether this is a retarded or advanced, doesn't matter. After impurity averaging, you get exponential decay in R as you increase the distance between any two electrons, and the Green's function after impurity averaging is a function of R decay exponentially with this characteristic mean-free path little l, and this little l is just Fermi velocity times this mean-free time. Okay, so you could consider a cartoon picture of this scattering event of this local impurity scattering potential like this. So electron come in and get scattered randomly by this randomly distributed impurity potential, and the average distance between any two collisions or scatterings is approximately given by the little l, and the little l is given by this Fermi velocity times the scattering time, or mean-free time. Okay? Okay, so this is another homework, a straightforward homework problem. You simply just perform this inverse Fourier transformation, taking you from this g k omega to g r omega, and looking at this spatial dependence of the g bar r omega, and you will see this exponential decay factor appearing because of this imaginary part of the Green's function right here. So we learned a lesson. The lesson is that whenever we have an imaginary part of the self-energy, this will lead to a quasi-particle decay, or the decay of your correlation function, or the Green's function. And you can also show that because of this imaginary part of the self-energy, and in time domain, this Green's function also suffer from exponential decay. Okay, and the decay rate is precisely 1 over 2 tau, or 1 over tau. So in other words, if you fix this g at a particular position r0, but you study the time dependence, and you can also see this type of behavior. So in other words, the Green's function, a single electron, decay exponentially both in time and in space. Okay? And so this is a very important lesson that tells us that interactions will lead to the breakdown of your quasi-particle picture. Namely, in the long distance limits, these two electrons do not have any relation at all because the correlation function decays exponentially. Okay? So they are related only within this finite range in time and space. Good. And same thing happened for different types of interactions such as Coulomb interactions or electron-photon interaction, and you name it. All these electron interactions will lead to a similar effect, that namely you get a finite lifetime of a quasi-particle.
So excuse me, the relaxation time of scattering rate here is two electrons collect to each other or electrons collect to the impurity?
Well, in this particular case, it is the electron scattered by the impurity potential. It is due to the single electron scattering off by the impurity potential, but in other cases, these interactions may be between any two electrons or any two spins, or between electron and photons. Okay? So there are many different types of interactions, but they have a common feature and consequence, and the common consequence is the existence of 1 over tau.
Can I think in a simple way? Since your impurity is a delta potential, so of course it's a short range. There's no reason it's become long range, right?
No, this is not related to whether these interactions are short range or long range. This short range potential is just approximation. Okay, the reason why we get this short range correlation is not because of the short range interaction or short range scattering potential. Okay, the nature of these interactions could be long range, short range, or whatever strange form you can imagine, but all of these different types of interactions will lead to the same conclusion, that you have a finite lifetime, not infinite lifetime. Okay, so you can relax the condition to consider a different shape of this your potential, a constant potential, potential barrier, whatever potential you like, and this qualitative feature will not change. All right, so this is the very generic feature of this quasi-particle decay in the presence of some sort of interaction potential.
And another thing is you told us it just shift the chemical potential, right? I mean, because for the triangular diagram, there's a real part of self-energy 0. So the first n equal to 1, that interaction shift the chemical potential.
Right.
But I think for the easy way to think that for the system, I add some impurity, of course the chemical potential will change, right? Because the number of electrons different.
Yes, you can say that. Okay, you could consider this as a consequence of you change the number of electron density. Okay, good. Right, so let me just make a plot to summarize this kind of a scattering induced relaxation rate. So if we plot imaginary part of a Green's function called the spectral function, it's retarded with a minus sign, something like that. So this is what you find. This imaginary part of your Green's function shows a broad distribution, and the width of this distribution in omega defines this scattering time. Yeah, so this is, suppose this energy epsilon k or ck, which is epsilon k minus mu, and you have a width of this spectral weight, or the imaginary part of the Green's function, over this in this omega axis, meaning your say spectral density is not a sharp delta peak in omega space, but rather a broad distribution. Okay, and the width of your peak defines this mean free time. It's precisely given by the mean free time. So, and you could very easily see that you could simply just plug in this G full right here, and you take the imaginary part of the G full after impurity averaging, and you plot it against omega, and you will see that it is broadened. It is not given by a delta peak. And remember, if there's no such imaginary part of the sigma, self-energy, so your free electron Green's function would look like omega minus epsilon k plus or minus I eta. Remember that. And for that, if you take the imaginary part by the Kirchhoff principle theorem, you get this delta peak, right? So this is called omega prime, right? So if there's just the I eta, where eta goes to 0 plus, then you get a sharp delta peak in frequency domain for a single non-interacting electron Green's function. But once we have such an imaginary particle self-energy, the consequence of this is the broadened spectral functions in omega axis, which means that this quasi-particle is not a very sharp located at a particular energy or frequency, but you can have a distribution of such a spectral function. Okay, so this is a byproduct of this scattering rate generated by this impurity scattering. Okay, so let's take a short break. When we come back, we will continue to think about this electrical conductivity and linear response theory and this kind of a fully dressed Green's function, and how can we go from the single electron propagator dressed by the interaction to the Anderson localization problem. Okay, so let's study another aspect of this problem which we ignored, which is the crossing diagrams that we neglected. Remember, we only consider a non-crossing triangle diagram, right? But what about this crossing triangles? And in particular, we could consider this kind of a two crossing triangles or three crossing or n crossing diagrams like this. And for two crossing triangles, you could actually twist this propagator around, and when you twisted this propagator in the middle, you'll get this interaction vortex, which looks like this type of this kind of a twisted propagator. In general, you could twist this many times, and when you consider many crossing triangles like this, so in general, you may define a twisted interaction vortex, which I defined as by Q, and then you could denote this, all this stuff inside the red circle by Q propagator, which is the wavy line right here, and then this wavy line connects this solid propagating line at these two different points, and in the intermediate stage, the electron propagates is actually against this initial and final state momentum, because this p prime, as you really twisted this propagator around, the direction of the p prime is actually against, is in the opposite direction of the p initial momentum, and also this opposite direction of this final momentum vector. So we don't have time to discuss the consequence of this diagram, so the lesson to be learned is that under certain conditions, and these diagrams could be neglected. Of course, they contribute, but under some conditions, and this conditions is this. So if, let me write it here. So epsilon f times tau is much larger than 1, which means that this tau is much larger than 1 over Fermi energy. Under such conditions, and these contributions, these diagrams can be neglected. And this condition tells us that the mean free time of this metal should be much larger than 1 over your Fermi energy. And this assumption is reasonably okay for ordinary metals. For normal metal, the mean free time is large. As a result, you don't need to worry about the other crossing diagrams. So this is the thing that we did not have time to justify, but you could verify this by looking at the reference books. So let's move on to the transport properties. So once we know the single electron Green's functions, and we could actually use this information to compute electrical conductivity, and which is the key quantity in the Anderson localization problem. So for that reason, we need to go back to this linear response theory and this Kubo formula that we introduced in the very beginning of this course. So let me just refresh your memory on this Kubo formula and linear response. Remember, we have defined this current correlation function in the very beginning of the course to justify the study of a Green's function. And back then, I mentioned that everything that you can measure in the lab is related to some sort of a Green's function. And here, we just illustrate this idea that this Kubo formula, which allows us to calculate electrical conductivity of a metal and within the linear response framework, and we'll see that this Kubo formula, when we derive this electrical conductivity, this is nothing but the current correlation function. So I will very briefly just refresh your memory on this. Suppose we applied vector potential A as function of R and T on any piece of metal or any material, and we can define this external part of the Hamiltonian, which is given by this vector potential dotted with the current operator. So this little j of R is so-called the paramagnetic part of the total current operator. And the total current operator, capital J, by definition, involves canonical momentum in the presence of electrical magnetic field. So I write this in a form that could be generalized to quantum mechanical operator very easily. So in real space and time domain, this capital J total is given by this delta function, which tells us where this current is flowing multiplied by this canonical momentum. And this is true both classically and quantum mechanically. So the quantum mechanical canonical operator is nothing but this momentum operator P minus this E times capital A, where A refers to this vector potential, but in second quantized form, this capital A is made of photon. Okay, so this is linear combinations of creating and destroying the photon. And then we could put it in the second quantized form. But this capital J is related to the little j by the following form. So this little j is just the current operator in the absence of this vector potential, capital A. Okay, but in the presence of a capital A, the capital J is the total current, which includes both the paramagnetic part of the current and also the contribution from the vector potential A. So
if you use a kind of a normalized unit, because the momentum unit is different from the current.
Of course, this unit is just this unit. So in many cases, all these universal constants are 1. H bar is 1, charge is 1, mass is 1. Yeah, of course. Yeah, you could use any units you like, but just to be consistent. So this little j in quantum mechanics is defined as this, where this psi refers to the creation, destroying as electron in the real space. So it could be decomposed in Fourier series like this. So this e to the ikr is just a Fourier coefficient, and ck is the destruction of electrons in k space. So you could just plug in this Fourier decomposition of this real space destruction operator back to this current operator, and you could show that this is given by sum of the p and q, e to the I q dot r, c dagger p plus q, c p dotted p plus half of q. So this is a standard form of a current operator, the paramagnetic part of the current operator, and I leave this to you as a homework exercise. And you can find this expression everywhere. All the standard solid-state condensed matter textbooks will actually define and have this expression. So remember, this operator or Hamiltonian right here is in the Heisenberg picture. So you get this relation when you time evolve this Schrödinger operator, and you get this Heisenberg operator. So it's a little j here. You could time evolve this Schrödinger current operator, the Heisenberg operator. And this is just a definition. So we could derive this linear response theory and we could get the corrections of the current due to the presence of the external vector potential, and the deviations of this current from the zero vector potential defines these little deviations of the current. You take the thermal average or ensemble average of these deviations of your current, and you find that this deviation of your current is proportional to this current correlation function. So we don't have time to continue today, but we will continue next week. So I guess that's enough for today.
Excuse me, your vector potential is a classical field or the...
Both. It is the same expression.
Okay, but I mean in the follow you will use the...
It doesn't matter. We don't second quantize it. So it looks classical, but you can second quantize this to make it a linear combinations of creating and destroying a photon.